Good afternoon. The course Applied Optics by NPTEL is officially over. The entire course of 12 weeks has been completed, and we have discussed assignment problems from each of those 12 weeks from previous year's questions. So, today's session is essentially a review session where we will revise as many concepts as possible which have been discussed in this course. So there have been 12 assignments, and we will go through as many as possible one by one and just revise and review the different kinds of questions that we have already attempted. So let us start with week 1. Okay, so there was one week 0 as well, which was consisting of some preliminary questions. So let us just review week 0. So light is, as all of you know, an electromagnetic wave with electric and magnetic fields oscillating perpendicular to each other and perpendicular to the propagation direction. So that's why electromagnetic wave is transverse in nature. So electric magnetic field perpendicular to each other and perpendicular to direction of propagation. And light exhibits both wave and particle nature. This we discuss more in the quantum theory. And when light passes through small apertures comparable to the wavelength of the light, then light bends, which is known as diffraction, and we have discussed the phenomenon of diffraction at length in this course. Diffraction from various apertures like circular aperture, rectangular aperture, from slits, from multiple slits. We have discussed all these cases. Okay, so now week 1. So we are just reviewing. We'll just go through all these questions once again, so that if you have forgotten, you would have a look at it again and recollect. So there will be no polls in this session. A wave satisfies the relation psi x comma t equals psi x plus minus lambda comma t. Then lambda is what? It's the spatial period of the wave, also known as the wavelength. So if you if you move by one period or one wavelength, then the wave repeats itself, as you can see from this diagram over here. So this is a question wherein we are given the amplitude and the wavelength, and then we have to find out the expression which represents the wave which is propagating along x-axis. So amplitude is 5 meters. That means the so this is the expression of the wave. Y is a sine kx minus omega t plus phi I. Phi I is the initial phase, which is 0 for our case. So amplitude A is 5 meters. And why kx minus omega t? Because the wave is propagating along x-axis. And k is 2 pi by lambda, and lambda we are given is 50 meters. So that's why 5 sine 2 pi x by 50 is the expression for the wave. Units of angular frequency is radians per second. Please note that hertz is the unit for frequency. normal frequency, not the angular frequency. Because the wave equation is linear, therefore we have the principle of superposition, which says that if psi 1 and psi 2 are two solutions of the wave equation, then psi 1 plus psi 2 is also a solution, or more generally, a psi 1 plus b psi 2 will also be a solution. Okay, and Huygens principle, as we have studied in detail, states that every point on a wavefront is itself the source of spherical secondary wavelets, and these secondary wavelets emanating from different points mutually interfere, and finally the sum of these spherical wavelets forms a new wavefront. The relation between the relation between speed of light in a medium and refractive index is given as follows. The refractive index is speed of light in vacuum over speed of light in the medium. Then we also learned about Fermat's principle, which says that a ray path would be one in which the time taken by the ray is extremum. Extremum means it could be maximum, minimum, or stationary. But for physical purposes, we consider minimum. Okay, if you have any doubt in any of these questions, please feel free to stop me, unmute yourself and ask the question, or you could put it up in the Zoom chat box as well. Again, a question making use of the definition for refractive index, which is speed of light in vacuum over speed of light in the medium. Ray path in a homogeneous medium means constant refractive index would be a straight line. In the last week, we saw graded index fibers where the ray path was a sinusoidal path. So graded index fiber is one in which the refractive index varies parabolically or quadratically, like refractive index is proportional to x squared if x is the spatial distance. Then we have also studied lenses and mirrors in geometrical optics. So whenever we study lens, we typically study about thin lens. And how thin is thin? So thin is when the thickness is small compared to the object, the image distance, and radius of curvature. So the way a lens behaves depends a lot on the refractive index of the material used to make the lens, as well as the refractive index of the surrounding medium in which the lens is kept. So typically, if we place a double convex lens in air, then it acts as a converging lens. But if we keep it in a medium in which the refractive index of the surrounding medium is greater than the refractive index of the material used to make the lens, then the same lens will act as a diverging lens. And how we see that? So this is the one in the red box is the expression for lens. It's the lens formula. So 1 over f is n2 by n1 minus 1 times 1 over r1 minus 1 over r2, where f is the focal length of the lens, n2 is the refractive index of the material of the lens, and n1 is the refractive index of the surrounding medium. R1 and R2 are the radii of curvature of the first and the second surfaces. And we need to keep the sign convention in mind whenever we are working with the lens formula. So the sign convention is anything above the principal axis is positive, anything below the principal axis is negative. Any distance in the direction of the ray is positive, and against the direction of the ray is taken negative. And when focal length is positive, we call it a converging lens, and when focal length is negative, we call it a diverging lens. Okay, so this was all for week 1. Very simple geometrical optics. I hope there is no question. I'll wait for a minute to see if there are any questions. Okay, so seems like there are no questions for week 1. Let us proceed towards week 2. So week 2 was on refraction and about lenses, as you can see. Oh, some questions we had not attempted in week 2. Maybe we can try and attempt them now. So, lot of questions on thick lenses in week 2. Okay, so let us revise this and let us fill in these gaps. So we learned the matrix method in week 2. So matrix method, let's look at this final expression. Matrix method is a method in which you can determine the output of any optical system given the input. And how you find this output? You find it by multiplying the input with some matrix, and this matrix represents the optical system. And the input is in the form wherein we have two numbers, lambda, which is the slope of the ray, and x, which is the distance of the ray from the principal axis, the height of the ray above the principal axis. So given the height of the ray and the slope of the ray, we can find out the output in the form of, again, height of the ray and slope of the ray by multiplying with this matrix. And for this kind of curved surface, we find the form of the matrix depends on the refractive indices as well as the radius of curvature. Okay, so, and P is nothing but power of the refracting medium. And in any geometrical optics system, we typically deal with paraxial approximation, And paraxial approximation is when the rays are very close to the principal axis. They make very small angles with the principal axis. So that is paraxial approximation, and matrix method works only in the paraxial approximation. And whenever we have the matrix given for any optical system, the A12 element is related to the focal length of the system as given by the expression in the red box. So A12 is minus 1 over f, or minus A12 is 1 over f. So f is basically minus 1 over A12. So given the matrix for an optical system, we can find out the focal length of the system. Now this question we had not completed earlier, so we will complete it now. For a sphere of radius 10 centimeters and refractive index 1.6, the focal length is what we need to find out. So let us solve. Radius 10 centimeters, so this is R. And what is the definition of focus? Focus is that point where the incident rays, parallel incident rays which are parallel to the optic axis, meet after refraction. After refraction from what? Refraction from the refracting element. So let us draw a sphere. That's my sphere. That's my principal axis or optic axis, passing right through the middle. And let us consider a parallel ray which is incident, then gets refracted in the medium, and then further gets refracted to meet at the point which is known as focus. So this point is the focus F. And from here to here, this distance is D. And for paraxial rays, in the paraxial approximation, D is approximately 2 times R, where R is the radius of the sphere. And let's call this distance V. Now we can see that refraction is occurring at 2 interfaces. This is the first point of refraction and this is the second point of refraction. So let us write down the matrix for the first refraction. As we saw in the first question, the matrix is given as follows, where P is and N2 we are given. This is N2 and this surrounding medium is air. And radius is 10 cm. this is the first matrix. Then we have transmission in the sphere, and the matrix for transmission is very simple. It's given as follows. And D is 2 times R, so 2 into 10 divided by N. This is N into, which is equal to N. This is my second matrix. And finally we have the second refraction, and after the refraction another transmission is there, so we have the second refraction. Now here the P would be reverse of this one. It would be 1 minus 1.6, because now N2 would be that for air, the second medium. This is the third matrix, and then we have another transmission to the focus. And since it is in air, the refractive index is 1 and the distance is V. Sorry, this is M3 third and this one is M4. Now the system matrix will be the product of all these matrices taken in the reverse order, because first the ray will encounter M1, then M2, then M3, then M4. So this is my system matrix. Let us write down. Now let us take product one by one. Product of these last two. I am making use of my calculator. Now again product of these last two using calculator. And finally the product Now we know that the output slope and height is m times the input slope and height, and for parallel incident the slope will be 0. And when we are at the focal plane, the height would be 0. And from this matrix equation we know x2 is the following, and from this matrix, system matrix, since x2 is 0 and lambda 1 is 0, since x1 can take any value, therefore we have this term equals 0, and from this we get the value of v. And this gives f, which is r plus v, because from the center we will look, this is my origin, so r plus v, which is r is 10 and v is roughly 3.33, so this is 13.33 centimeters. So the correct option is option A. Note that we could also find it from another method by using this element over here. So we know that from system matrix, and this is A12, we know that 1 over f is minus A12. We saw it in a previous question. This is important. So, and A12 is, we know, is this. So this is, from this we get from here again we get the same. So this and this both give the same result. Okay. Oh, I left too much extra space, or maybe I wrote this time too small. Anyway, moving over to the next question. We have two thin convex lenses of different focal lengths, and they are separated by a certain distance and they are placed coaxially, and we want to find the focal length of this system. Again we will use the same matrix concept. So for the first lens, the matrix, this is the matrix for lens. So a system matrix would be lens 2 times the transmission between the lenses times lens 1. Transmission is very simple. T is the distance of transmission. Multiplying now we will look at this. This term gives us the focal length. This is A12, which is minus 1 over f. So we get 1 over f equals 1 over f1 plus 1 over f2 minus t over f1 f2. So important expression. We know f1, f2 and t. So we get it 1 over 10. Separation is what? 20 centimeters. This is t. Everything is in centimeters. Correct answer is 15 centimeters. Option C. Again, we are asked to find out the refraction matrix. And we know for a refracting surface, the matrix is given as follows, where T is the power. Power meaning N2 minus N1 over R. The focal length for a combination of two thin lenses of focal lengths f1 and f2 separated by a distance d is what? We just found out from this expression. It is 1 over f1 plus 1 over f2 minus t is the transmission, means the separation distance over f1 f2. Here the separation distance is d, so it will be d over f1 f2. Note that option D is dimensionally incorrect. In fact, inconsistent. Because the first term is d over f1, which is dimensionless. D has dimension of length, f1 has also dimension of length, so it is dimensionless. Whereas the last term has dimension 1 over length, because it is d over f1 f2. Nodal planes coincide with the unit planes when media on either side of an optical system have the same refractive index. Another question for finding out the system matrix for transmission. The transmission system matrix is very simple. It just depends on the distance of transmission and the refractive index of the medium in which the transmission takes place. Focal length of a thick lens is given as what? So let us derive the expression for the thick lens. This is the last question for week 2. So what exactly is a thick lens? So a thick lens, will look somewhat like this. This is exaggerated version, but this is to explain. So if we have some ray, then it encounters refraction at the first surface, and then refraction at the second surface. So this is the first surface where refraction takes place, and this is the second surface where refraction takes place. And this medium has refractive index n, and this thickness is t, and it is kept in, let's say, air. So let us write down the system matrix. So for first refraction, this is the system matrix where P1 is the power. So R1 is the radius for the first surface, R2 for the second surface. Then we have transmission. And then second refraction. So the system matrix for this thick lens would be second refraction times transmission times first refraction. So M is what? Let us just plug in. Taking the product, final product, and we know that this A12 term gives the focal length. So we have 1 over F equals minus A12, which is P1 plus P2, 1 minus TP1 over N. Let us plug in the values for P1 and P2. So this gives us the final result. So the correct option is option A. Note that in this expression, if we put T tending to 0 for thin lens, we recover the usual expression for thin lens. So it is consistent. This was about week 2, matrix method. Now we can move to week 3. Wavefront is the locus of all points which are in same phase. A wave whose electric field oscillations are confined in one plane is called plane polarized. And then we discuss some examples of polarization: linear, elliptical, circular. And this was the general case where we the general expression, and if we plug in the special values for this epsilon, then we get linear or elliptical, right-handed or left-handed. So this general expression is very useful when we are trying to find out the polarization for a given case. For example, here we are given two waves Ex and Ey, and we are asked to find out the polarization of the resultant. So let us review this, how to find out for the general case. So we have two components, Ex and Ey. Ex is along the x-axis, Ey is along the y-axis, and they have certain phase difference between them. So let's say Ex is having phase difference epsilon with respect to Ey. That's what we are taking over here. And from this we take the ratio and do some simple algebra to get this general equation of an ellipse. And if we plug in some particular values of epsilon, then we get either linear or elliptical. So in this case we get linear because Ey over Ex is a constant. It is a fixed constant which is -1, so slope is -1. According to Huygens theory, speed of light in a denser medium would be lesser than that of a rarer medium. And this we can see from this expression. Speed of light in a medium is equal to speed of light in vacuum over refractive index. And for a denser medium, the refractive index is higher as opposed to that for a rarer medium. As a result, the speed of light in a denser medium would be lesser than that in rarer medium. And just to recollect, Huygens theory states that every point on a wavefront is itself the source of spherical secondary wavelets, and these secondary wavelets emanating from different points mutually interfere. And finally, the sum of these spherical wavelets forms a new wavefront. If a wave gets refracted into a denser medium, which quantity remains invariant? The quantity which remains invariant is frequency, which is a property of the source. Both the speed and wavelength change according to the refractive index. So speed of light in medium is inversely proportional to refractive index. Also the wavelength of light in medium is inversely proportional to the refractive index. Phase difference is 2 pi by lambda times path difference. This is a very important relation. In a homogeneous isotropic medium, polarization is associated with the direction of electric field vibration. Whenever we say polarized along the x-axis, that means the electric field vibrations are along the x-axis. So when the magnitude of electric field vector remains constant, then such a wave is circularly polarized. Because in linear polarization, the magnitude of electric field vector will vary. It will vary sinusoidally. It will vibrate in the same direction, but the magnitude will vary. As you can see here, I have discussed. So in circular polarization, the magnitude remains constant. In linear polarization, the magnitude varies sinusoidally with time, and even in elliptical polarization, the magnitude varies with time, and it's this complex kind of complicated looking expression. In a homogeneous isotropic medium, plane of vibration contains propagation vector k and the electric field vector E. The relation between phase difference and path difference we saw earlier is such that phase difference is 2 pi by lambda times path difference. So if the phase difference is doubled, then the path difference would also be doubled. Then I had shown you some simulations on beats and wave packets. So beats is when we add up two waves having very close frequencies. So when we add up two waves having frequencies very close to each other, we see this variation which is called beats. We have this product of two waves, one having higher frequency which is omega 1 plus omega 2 by 2, and another one with the lower frequency which is omega 1 minus omega 2 by 2. So we see that the higher frequency wave is modulated by the lower frequency wave. And wave packets is just a result of principle of superposition. It is adding up many different modes with different proportions. And wave packets are more localized in space, so they are a better representation for a particle. So in week 4 we were introduced the concept of interference and Young's double slit experiment. What kind of pattern is observed when two coherent orthogonally polarized plane waves interfere? So orthogonal polarized plane waves will never interfere. As a result, you will not see any interference fringes. You would only see uniform illumination. And here we had derived the general expression in terms of the which incorporates the polarization as well. So delta is the phase difference between the waves and theta is the polarization. The polarization difference with the angles the two waves make with each other. So we see that when theta is 0, we have parallel polarization, and for theta 90, we will not see any interference. We will just see uniform illumination I1 plus I2. What kind of pattern is observed when a plane wave interferes with a spherical wave, that is circular fringes? Again, we had done this long derivation of adding up a plane wave with a spherical wave and looking at the resultant intensity. And the resultant intensity has this cosine squared term, and the argument of the cosine squared has this x squared plus y squared term. As a result, we see circular fringes. So we are just revising whatever we have already studied. When two polarized coherent waves of irradiances I1 and I2 having phase difference delta phi superposed the resultant irradiances, we had just derived the general expression over here. So I have written it over here again. And for parallel polarization, theta is 0. So we have I1 plus I2 plus 2 root I1 I2 cos delta phi. Two beams produce a sustained interference pattern when they have same frequency. We saw in the previous week for different frequencies we had beats. So beats, the amplitude keeps varying with time. So that will not give sustained interference pattern. In Young's double slit experiment, a laser light passes through two identical and parallel slits. So we are given basically the distance between the slits and the screen, and we are also given the slit separation and the fringe width, and we are asked to find the wavelength. So the relation between all these quantities is given as follows, that the fringe width is wavelength lambda times distance between slit and screen capital D over A, which is the slit width. Sorry, not slit width, slit separation. So given these quantities, we can find out the wavelength. So here, this is the expression for the interference intensity. Imax is the maximum intensity which will happen when the phase difference delta is 0, and Imin is the minimum intensity which will happen when the phase difference delta is pi. And then we are given the amplitudes I1 and I2, and we are supposed to find out the ratio Imax over Imin. Okay, so someone is asking what happens when I1, I2 are same. So that is what I have written over here in this right hand side small margin. So when I1 equals I2 equals I naught, then the intensity becomes 4 I naught cos squared delta by 2. And the maximum intensity in this case is 4 I naught and minimum intensity is 0. Two harmonic light waves with amplitudes we are given, and the electric field vectors are perpendicular. So perpendicular meaning there would be no interference fringes, they are orthogonal. Orthogonal polarizations give uniform illumination I1 plus I2. So uniform illumination, so Imax equals Imin equals to intensity for any other phase difference, because it is constant, so the ratio will be 1. For obtaining a maximum in Young's doubles for in any interference, the path difference should be an integral multiple of lambda, the wavelength. And in Young's double slit experiment, the path difference is the slit separation times the distance on the screen divided by the distance between slits and the screen. So when we have white light passing through Young's double slit experiment, we see colored fringes. And the central band is always white because that is the point where we have constructive interference for all the different wavelengths. So that's why the central band is white, and after that we will see a few bands which are colored, and the color would be such that first we will see violet, then indigo, then blue, then green, then yellow, orange, and finally red. So as the wavelength increases, the fringe width also increases. So when we cover one of the slits in double slit experiment with some sheet like mica sheet, then the interference pattern remains same. I mean, the fringe width remains the same. Only thing that changes is that the fringes get shifted. So the central fringe gets shifted by a certain distance, and this distance depends on various parameters, and these parameters include the thickness of the film, the refractive index of the film, distance between the screen and the slits, and the slit separation. So here we are just finding out the thickness of the film, which causes a shift by some delta. And how we find out this experimentally? So if we use white light, then we know that the central fringe is white for white light and the other fringes are colored. So we will use white light and then the mica sheet, and then we will find out where we see that white band, and the distance from the origin to that white band would be the shift. Then I had shown you a live demo of Young's double slit experiment. You can go back and check that video. Okay, now week 5. So in week 5 we discussed various other interferometers like Michelson interferometer, we saw Newton's rings experiment, we saw thin film interference and Fresnel's biprism, all these different setups from which we can observe interference effects. So Young's double slit experiment is an interferometer which works on the principle of division of wavefront. Michelson interferometer and Newton's ring interference are based on division of amplitude. So whenever a monochromatic wave is incident on a transparent film, then we see some part getting reflected and some part getting transmitted, and the frequency remains the same, or however the amplitude would be different based on the reflection and transmission coefficients. Soap bubbles look colorful because of interference of light, and in particular this is thin film interference. Thin means the thickness is of the order of the wavelength. Whenever we have a thin film, then the optical path difference between the waves reflected from the first surface and the wave reflected from the second surface depends on the refractive index of the film, thickness of the film, as well as the angle of transmission. And here we have found out that expression, and the path difference comes out to be 2nd cos theta t plus minus lambda by 2. This lambda by 2 is because one reflection occurs from a rarer to a denser medium, which causes a phase shift of pi, and phase shift of pi corresponds to a path shift of lambda by 2. And theta t can be found out from theta I, and theta d is the angle of transmission. So 2nd cos theta t plus minus lambda by 2. Fringes of equal thickness appear in Newton's ring experiment. Which is an interference experiment based on division of amplitude. Young's experiment, double slit experiment, and Fresnel's biprism are based on division of wavefront. Physiofringes appear when the thickness of the thin film is non-uniform. So physiofringes are fringes of equal thickness, which are basically rings formed for a particular thickness value, and this occurs for a wedge film interference as well as for Newton's ring interference. The other type is Heidinger fringes, which are fringes of equal inclination, which is basically rings formed for a particular inclination angle, and this happens when we have a uniform thin film. So whenever the path difference is less than the coherence length, we see strong interference. However, if the path difference is greater than the coherence length, then we see very weak interference. Here I have just written down the reflection and transmission coefficients based on the refractive indices of the medium on either side of the interface where the reflection and transmission takes place. And you can look into this book, Introduction to Electrodynamics by D.J. Griffiths, for the derivation of these expressions. Newton's ring experiments, as we have already discussed, relies on interference by division of amplitude. And why? Because we see reflection at two different interfaces, which leads to division of amplitude, because reflection and transmission cause a change in amplitude. Radius of the rings in the Newton's ring experiment depends upon radius of curvature of the convex lens, wavelength of light, and the refractive index of the enclosed film. And here we have derived the expression. So here is the expression where x is the radius of the ring, and we see it is depends on lambda, capital R and n, and m is the order of the ring, of the fringe, of the bright fringe. In Michelson interferometer, if the path difference between two mirrors is decreased, then the fringe pattern will shrink towards the center. And here we have just discussed how a Michelson interferometer works. This is week 6. In week 6, we studied the Fabry-Perot interferometer in quite some detail and different terms and parameters related to the Fabry-Perot interferometer. If the mirror reflectivity in a Fabry-Perot interferometer is increased, then the transmission peak becomes sharper. And here we have just derived the reflection and the transmission intensities. And how they depend upon the reflectivity of the mirrors. Small r over here is the reflectivity of the mirrors. So as we can see that if we increase the value of f, which is the coefficient of finesse, then we observe sharper peaks in the transmission spectrum, and increasing the value of f can be achieved by increasing the value of r, which is the reflectivity. Similarly, in the reflection spectrum, we see dips, and the sharpness of the dips increases as the coefficient of finesse increases, which in turn increases when the reflectivity increases. Apart from coefficient of finesse, we also have a term called finesse. Now, finesse is proportional to coefficient of finesse, and the relation is pi square root f by 2. Then we also have a term defined, which is the free spectral range, which is based on the concept of Rayleigh's criterion for resolution. Then coherence length and coherence time are related. So coherence length is speed of light times the coherence time, and coherence time is inversely proportional to the bandwidth. And we have derived the relative transmittance intensity as well as the relative reflectance intensities for the Fabry-Perot interferometer in detail over here. So the coefficient of finesse can be increased by increasing R, which is the reflection coefficient, which increases when we increase the reflectivity of the mirrors, and finesse is proportional to coefficient of finesse. So if we increase the reflectivity, we increase the finesse. Then another question on free spectral range. Here we are given the reflection coefficient, and then we are asked to find out the coefficient of finesse, and this is the relation 2r over 1 minus r squared whole squared. And half width is inversely proportional to the square root of the coefficient of finesse. Moving on to week 7. In week 7, we discussed Fraunhofer far field diffraction from different apertures. Bending of light as they pass by some object or through an aperture is an example of diffraction of light. Diffraction phenomenon can only be explained on the basis of wave model of light. And Huygens principle is not able to explain diffraction phenomenon. However, if we incorporate the Fresnel's modification to Huygens principle, then we can explain the phenomenon of diffraction. So Huygens Fresnel principle states that every unobstructed point on a wavefront at a given instant serves as a source of spherical secondary wavelets. The amplitude of the optical field at any point beyond it is the superposition of all these wavelets. So the diffraction pattern is inversely proportional to the slit dimensions. So a slit of certain width is used in a single slit experiment. If the slit width is reduced by half, then the diffraction pattern becomes 2 times wider. In the Fraunhofer diffraction regime, the effective distances of source and screen from the aperture would be infinite. So in Fraunhofer regime, it is called far field regime because screen is placed very far away from the aperture. And this can be achieved by making use of lenses. So if the source is kept at the focal plane of the lens, then we will get parallel rays out, and then these parallel rays fall on the screen, fall on the aperture, and after the aperture we place a lens and the screen would be at the focal plane of the lens. In the double slit diffraction, width of each slit is increased by the same amount, keeping the center to center separation between the slits constant. Number of fringes within the central diffraction peak will decrease. So double slit diffraction is essentially like a product of single slit diffraction and Young's double slit interference experiment. So the slit separation controls the Young's double slit pattern, whereas the slit width controls the single slit diffraction. So if the slit width is increased, then the central peak width would decrease. As a result, we will see less number of fringes within the central diffraction peak. Also, if the slit separation is increased, keeping the slit width constant, then the number of fringes in the central diffraction peak will increase. Why? Because if we increase the slit separation, then the fringe width for the Young's double slit part decreases. Fringe width decreases, that means the fringes are closely spaced and we will see more number of fringes within the central diffraction peak. So here is a question on the single slit diffraction. So the intensity expression is given over here. For single slit, it is I naught sine beta over beta whole squared, where beta is kb sine theta by 2 and b is the slit width. And for double slit diffraction, it is 4 I naught sine beta by beta squared times cos squared alpha. So sine beta over beta squared is the single slit diffraction part and cos squared alpha is the Young's double slit interference part. So beta is kb by 2 sine theta, where b is the slit width, and alpha is ka sine theta by 2, which is where a is slit separation. Missing order occurs in a double slit diffraction experiment when interference maximum and diffraction minimum corresponds to the same angular position. Interference maximum meaning the Young's double slit interference part, and diffraction minimum meaning the single slit diffraction part. Then in week 7 we had discussed some uh, problems from week 6 as well, but here we have not solved, so let us solve it now. So visibility of the fringes is a direct measure of the degree of coherence, and let us see how. So the electric field will be a superposition of the fields from 2 points. The intensity is mod expectation of the mod E squared. Now if we have two complex numbers, let's say a is x1 plus I y1 and b is x2 plus I y2, then a star b plus b star a, let's see what that is. So we see that some terms cancel, this term cancels out with this term, this one with this one, so we get this. So using this is basically what this is, 2 times the real part of a star b. Because a star b is this and the real part is x1 x2 plus y1 y2. So putting it over here, where gamma is the complex degree of coherence, and visibility and I max is when is this case with the plus sign, and I min is this destructive interference. So this then turns out to be And we see that visibility is directly proportional to the degree of coherence. And if we have I1 equals I2, then in that case visibility is equal to the degree of coherence. The finite coherence time of a source could be due to finite lifetime of energy level, random motion of the source, and collision with another atom. All of these. Coherence time of a source is given. The coherence length we can find out, very simple. So coherence time is 10 to the power minus 9 seconds given. So coherence length is c times tau c, which is 0.3 meters, which is equal to 30 centimeters. Option B. Spatial coherence is associated with extent of the source in space. Temporal coherence is associated with finite bandwidth of the source. In fact, coherence time is inversely proportional to the bandwidth. Two sources are coherent only if phase between the sources remains same with time and space. So that was all. Next, moving to week 8. In week 8, we were introduced to diffraction gratings and circular apertures, Rayleigh criterion, and different terms related to a diffraction grating. A diffraction grating is repetitive array of either aperture or obstacles. So it's a repeating array of many slits. You can think of it as multiple slits, and the order is like thousands of lines per inch. The radius of the first dark ring produced from an aperture of diameter d, when we have lengths of focal length f, is 1.22 lambda f by d, and here we are just deriving it. And this pattern is called the Aries pattern. It's like concentric circular fringes. Here is a simple numerical based on that. Radius of the first ring is 1.22 lambda f by d. First dark ring. According to Rayleigh's criterion, to just resolve images of 2-point sources, one requires the center of one Airy disk pattern to fall on the first minimum of the Airy pattern of the other point source. This is just a schematic. And to increase the resolution, we need to then decrease the wavelength. So if we decrease the wavelength, then the least separation for resolving also decreases. So we can resolve better. So if the spatial separation for minimum resolvable distance is 1.22 lambda f by d, then the minimum resolvable angular separation would be 1.22 lambda over d. For normal incidence, grating spectrum is A sin theta equals m lambda. And here we are just using a simple expression to derive it. And grating is essentially multiple slits, so we can use the multiple slits diffraction intensity formula. Resolving power of the mth order spectrum of a grating is m times n, where n is the number of slits. Free spectral range for diffraction grating is lambda over m for the mth order. And resolving power of a grating cannot exceed 2 Na by lambda. N is the number of slits, lambda is the wavelength, and A is the slit separation. So if we increase the order of the diffraction, then we increase the resolution. We saw it over here. Resolving power is m times n, m is the order, but the upper limit of that resolution is over here. Fraunhofer diffraction is valid for this approximation, and Fraunhofer approximation occurs when we are in the far field regime, so we neglect some quantities and based on what we neglect is how we come up with this regime for Fraunhofer approximation. So distance z should be much larger than the aperture dimensions. Now week 9. Week 9 we were introduced to the concept of Fresnel diffraction and Fresnel half period zones. Obliquity factor was introduced to prevent back propagation of wave by the Huygens-Fresnel principle, and the expression is 1 plus cos theta by 2. So when theta is pi, the obliquity factor is 0, which means no back propagation. All the point sources within the area of a Fresnel zone are coherent. Zero value of obliquity factor signifies energy is not propagating in backward direction. And Fresnel zone is also known as half period zone because phase difference between successive zones is pi, which is half a period. One period is 2 pi. So if a Fresnel zone is divided into 5 subzones, then the phase of each subzone would be pi by 5 because each period has phase of pi. So if there are n subzones, phase of each subzone would be pi over n. And phase difference between the center of the first Fresnel zone and the edge of the second Fresnel zone is 2 pi because pi for each zone. Last Fresnel zone does not contribute to the vibration curve because obliquity factor is 0. And Fraunhofer diffraction pattern is observed when the Fresnel number NF is much less than 1. So NF less than 1 means very small number of Fresnel zones are in aperture and we are very far away from the aperture. If we move far away from the aperture, the number of Fresnel zone decreases. If the first Fresnel zone is obstructed by the circular disc, then the amplitude of the field at the point of observation remains same. This comes from the Babinet's principle, which says that we see same diffraction pattern for obstacle and aperture of same shape and size. In week 10, we were introduced to concepts of polarization, the Brewster's law and Malus law, and also birefringent crystals. So Brewster's angle is tan inverse n2 over n1, where n2 is the refractive index of the second medium, n1 is refractive index of the first medium. And at Brewster's angle, the reflected beam is completely polarized with polarization perpendicular to the plane of incidence. In a birefringent medium, ordinary ray follows Snell's law, extraordinary ray does not follow Snell's law. And a typical example of a birefringent medium is calcite. And here we have just written down the expressions of speed for ordinary and extraordinary rays. Theta is the angle between E ray and optic axis. And along the optic axis, the speed for both ordinary and extraordinary rays are the same. So according to Malus law, the output intensity is input intensity times cos squared theta, where theta is the angle between the transmission axis and the polarization of the input beam. And if unpolarized light falls on a polarizer, then the output intensity would be simply I naught over 2. A polarized light cannot be produced by interference. Here is a simple numerical as an application of Malus law. Again, Malus law states that the output intensity after a polarizer is the input intensity times cos squared theta, where theta is the angle between the linear polarizer transmission axis and polarized light polarization. So when an unpolarized light is launched at Brewster angle at an interface between two media, then the reflected light is polarized and the polarization is perpendicular to the plane of incidence. And also in this case, the refracted light is partially polarized. And we can increase the degree of polarization of this partially polarized refracted light by having multiple interfaces, and such that at each interface the ray is incident at the Brewster angle. This way we can increase the degree of polarization. Also at Brewster angle, the reflected and the transmitted rays make an angle 90 degrees with each other. So theta I plus theta r is 90 degrees. Theta r is the refracted angle and theta I is the incident angle, which is also the same as the reflected angle. When a circularly polarized light of intensity I naught falls on a polarizer, and if the polarizer is rotated with some angular frequency omega, then the output intensity remains the same. It does not vary with rotation. And the output intensity is simply I naught over 2. In a uniaxial crystal, ordinary and extraordinary rays have the same speed along one direction, and that one direction is called the optic axis. In week 11, we were introduced to phase retarding plates called like quarter wave plate and half wave plate. In a negative crystal, NE is less than NO, where NE is the refractive index for the extraordinary ray and NO is refractive index for the ordinary ray. If NE is greater than NO, then it is a positive crystal. Quarter wave plate introduces phase shift of pi by 2 and path difference of lambda by 4 between the components parallel and perpendicular to the optic axis. And half wave plate introduces a phase shift of pi and path difference of pi lambda by 2. If the electric field E and the electric displacement vector D are pointing in different directions, then the medium is said to be anisotropic. And here, epsilon, the relative permittivity, is a tensor which is represented by a matrix. This is a simple numerical for finding out the thickness of the crystal to generate a particular phase shift between the components, and this is for a half wave plate. So the thickness depends on NO and NE as well as what phase shift you want to generate. Here we see that for extraordinary rays, the E means there is an angle between the pointing vector and the wave vector. Whereas for ordinary rays, that angle is 0. So the answer to this question 8 is all of these. A Polaroid is introduced in the path of the beam and Polaroid is rotated about the direction of the propagation of the beam. If there is no variation in intensity, then the light beam can be circularly polarized, it can be unpolarized, and it can also be a mixture of unpolarized and circularly polarized light. And we can distinguish between these three cases A, B and C by adding another quarter wave plate and a polarizer after the first polarizer. And based on the outcome after the second polarizer, we can distinguish the different cases. Similarly, answer to this question 9 is also all of these. If when a Polaroid is introduced in the path of the beam and Polaroid is rotated about the direction of the propagation of beam and if there is no variation in intensity, if there is a variation in intensity without complete extinction, then the light beam can be elliptically polarized, mixture of linear and unpolarized, or a mixture of elliptically and unpolarized light. Again, we can distinguish between these three cases by introducing another quarter wave plate followed by a polarizer. When we send in a circularly polarized light through a quarter wave plate, the output light would be linearly polarized. And I just introduced a concept of Jones calculus, wherein we have matrices for different elements of polarization, like matrix for quarter wave plate, matrix for half wave plate, matrix for a linear polarizer, and we represent the linearly polarized or circularly polarized light as a vector, and then we find the output as a product of the matrix and the vector. And finally, the last week, which I hope you would not have forgotten because we discussed it last week itself, In the last week, we were introduced to many concepts like anti-reflection coatings, optical fibers, holography, and lasers. This is a question on critical angle. The angle of refraction of a light ray launched at critical angle would be 90 degrees, and this critical angle is sine inverse n2 over n1, where n2 is the refractive index of the second medium and n1 is the refractive index of the first medium, and this happens when we move from a denser to a rarer medium. Phenomenon responsible for light guiding inside optical fiber is total internal reflection. And numerical aperture of the optical fiber is simply n2 squared minus n1 squared, where n2 is the refractive square root of that, where n2 is the refractive index of the core and n1 is the refractive index of the cladding. Dispersion is the phenomenon which causes each wavelength to take different amount of time to propagate along the same path. This happens because refractive index is a function of wavelength. In fact, it is inversely proportional to wavelength according to Cauchy's equation. Population inversion cannot be achieved in a two-level system. At best, we can achieve the case of 50-50 population, like n1 becoming approximately equal to n2. But we cannot achieve population inversion in two-level systems. We can have population inversion in 3 or 4-level systems. For example, ruby laser, which is a 4-level system laser and which uses xenon or krypton flash lamp for pumping. And pumping is to pump the atoms to higher energy level to create a situation of population inversion. The output wavelength of ruby laser is 6943 angstroms, which is like in the red color region. Lasing action starts only when we achieve population inversion for the amplification. Anti-reflection coatings work for a particular wavelength, and if the refractive index of the anti-reflection coating is given, and if the wavelength for which we want no reflection is given, then we can find out the particular thickness. Only for a particular thickness we will achieve this anti-reflection feature, and that is given by thickness d equals lambda over 4 nf. If we deviate from this lambda, then we do see some amount of reflection. If we deviate too much, then we will see significant reflection. Hologram records amplitude as well as phase information of the object. So that's all. This brings us to the end of the review session. So today is finally the last class. After this, you will have just the final exam for this course, and I hope all of you do well in the final exam. If you have queries right now, you could ask in the Zoom chat box. And if you get some queries afterwards, then you can make use of the discussion forum for this course. And also you can put up your queries in the YouTube channel for this course. I will put it up in the Zoom chat box. So this is the YouTube channel where you will find the recordings to all previous live problem solving sessions. So you could watch them to review. And if you have any question, you could post it as a comment in the YouTube channel for any particular video. So, okay, thank you very much. Bye bye, and all the best for your final exam. Hope all of you do well and score good marks. Hope you all enjoyed this course. Bye.